Good afternoon, everyone. How are you guys doing? Doing all right? Good. A few things. Remember that this week there is a laboratory going on. Those of you that already did the lab, it was a cool lab, wasn't it? It was very good, you see. So those of you that have still to do it, you'll see that it's a nice one. You're going to have to play with the load frame, with the pumps, with the fluids, with valves, with O-rings, with vacuum grease. I think that's a lot of fun. I don't know you, but to me, that's a lot of fun. So, but what I wanted to tell you is that remember that you need to show up in the laboratory with long pants and with closed-toe shoes, all right? That's very important for safety reasons. All right. I wanted to do a very quick review of last class because when I recorded on Friday, somehow the audio was not working, so there is no audio at all. And I just wanted to go very quickly through what we talked about. So we discussed about strength and isotropy, and we said that rocks, because especially sedimentary rocks, because of the way they are made, they are strongly anisotropic. And it's not the same if you fail a rock perpendicular to bedding, or if you fail it parallel to bedding like this one, or at an angle. The rock is going to be stiffer or softer, depending on which direction you test it, and also the strength is going to be different. And the way it breaks is going to be different too. And how it breaks then is going to affect, for example, how you drill a wellbore or how you make a hydraulic fracture. And after that, we put together something very important. And here we discuss that for a given in situ state of stress, the rock may be happy, maybe not at failure, but then we can cause different actions, we or nature, in which we can get the rock to tensile failure to the left, to shear failure to the top or to the right or in this direction. Anywhere you go in this direction or in that direction, you go to shear failure. And last, if you go too much to the right with not probably a lot of shear but quite a bit of compression, you get to the compression yield failure. And we will not talk much about the compression yield, but you should know that compression yield failure, it is there. All right, and after we talked about strength and isotropy and the compression yield, we talked about the transition of rocks failing in brittle fashion to ductile. And what that means is when the rock is brittle, it breaks into very well-defined failure planes. When it's ductile, it's more like it flows. Sometimes you can see some small fractures, sometimes you cannot. And when you look at the stress-strain curves, that looks from something like goes through a very well-defined peak to something that rolls over, and sometimes it may never reach a maximum. The perfect ductile failure would be a failure in which it increases up to a point and then it just continues yielding at a constant value. And we discussed a little bit about the factors that affect this brittle to ductile failure. One of those, the main one, mean effective stress. That means when we go deeper, the rocks get more ductile. Temperature, also higher the temperature, the higher the ductility. When also we get deeper, rocks get more ductile. And time is also important. And I was thinking about something here, as Mr. Barakia suggested. Here also we should put for shales, and especially for organic shales or oil and gas shales, is that the bigger the TOC and the bigger the amount of clay, also the bigger the ductility. And this is something very important because some of the advantages of, for example, having a brittle rock is that it fractures more easily. It creates more specific surface when you fracture it. Opposite to something which is ductile, that when you fracture it, you will create just one single fracture. And we're going to see later on that that is very important. And a part of that brittleness, which is kind of a loose concept, let me tell you that, but at the same time, it captures many things. At the end of the day, what we want to do is increase surface area in hydraulic fracturing, and some of that will come from shear failure and fracture reactivation, which is what we're going to see right now. Okay, so we're done with this part, and also we're done with, I think it is chapter number 4. Now we're going to start talking about a new topic, which is the topic of faults and fractures. All right. So you remember what were the factors that affect ductility? Temperature, and which other one? Time. And there was one more. And depth in terms of confining stress. Well, it turns out that, you know, when you go deeper, it gets hotter, you have more pressure, more stress. If you go very, very deep, you get to magma, and you get to siliceous compounds are just like magma, and it just flows, right? It's a liquid more than a solid. But as you get closer to the surface, you have less stress, you have lower temperature. All of these elements, they start to solidify and they form rocks. And on top, on the surface, we just have this brittle crust, which is the lithosphere, which is actually cracked. And that's why we have tectonic plates. We have tectonic plates because this lithosphere, it's divided in plates. And these are some major regions in which the lithosphere, it may open up or may converge or may go into sort of a shear failure, like for example, some over here. But those are the major ones. Inside the plates, because of these movements, we have also folding and faulting. And folding would be more a type of a ductile failure of the shallow crust, but sometimes this shallow crust is also going to fail. And it's going to fail through faults, among other failures. And this is very similar, probably, if I show this picture, you will remember what I mean. Do you guys know where to get a good creme brulee? Here in Austin? Do you don't know? Well, there is a very good place, kind of pricey, so but it's a very good place. It's called Justine's. It's on 5th Street, East 5th Street. The creme brulee there is pretty good. I was there yesterday. I didn't get creme brulee though because I'm on a diet, but it is the lithosphere. Let me look for a good picture. The lithosphere, it's like this creme brulee, in which underneath it's sort of liquid, but then when you crack it, and that is the best part of eating the creme brulee, right? When you crack it with a spoon, it is brittle on the surface and it cracks, it breaks, and those failure planes, in our case, are going to be faults. And we want to understand what those faults are, how they form, and also how those limit the state of stress, and how those also play a factor on telling us the direction of stresses. We have seen that the direction of stress is very important. And for example, in many cases, is going to tell us what is the direction in which you have to drill a horizontal well for doing hydraulic fracturing. And let me go straight to the homework here, just to show one example that we're going to take a look later on. So you see an example of this. Here, what do we see? We see south of Texas. Here is the Eagle Ford Formation. And these lines that you see over here, those are faults. Those are the lines of faults, major faults that you can map with seismic data. And we'll see that the direction of these faults, look how well aligned they are. The direction of those faults has a lot to do with what we have here and the state of stresses over there. Okay, so let me see if I forget anything. No. Okay. So then the idea is that as we get closer to the surface, rocks start to melt. They become more brittle, and as they become more brittle, they fail. And sometimes they fail as a fault. But what is a fault? A fault is just shear failure. And we have seen what shear failure is. You have done the test. We have characterized that. And with this example, hopefully you will remember that a fault is just an event of shear failure. So let's imagine that you have a sedimentary rock, and a long time ago, you had this rock somewhere over here, and it's supposed to be a T-Rex. Okay? And then after time, we know that tectonic plates move. You guys are aware that the continents, they have changed shapes a lot during millions of years, and with that change of shape and all of those movements of the tectonic plates, you may have added significant stresses on this lithosphere. And if you add stresses, the point here is that you cannot add stress on this direction, in this case horizontal direction, forever. At some point, this rock is going to break. And the way that it's going to break, just by the action of stresses with one larger in one direction than in the other direction, is going to be shear. And basically, what we're going to have is that after some time, this rock is going to fail. Probably the rock that was before somewhere over here, it might have gone down in this direction. Usually in fault terminology, this is called the foot wall. Whatever is underneath the fault is called the foot wall. And what was on top is, does anyone know how this one is called? It's from your geology class. Hanging wall, very well. It's called the hanging wall. And it goes up with respect to the previous one. And remember that in this case, we're assuming that we are adding a horizontal stress in this direction. Over a long time, we may have this rock to weather and to erode. So this thing is going to disappear. And maybe, let me leave the shape that it had before. And here you may have, after some time, a river over there or something like that. So that's simply a fault. And And we are going to study about how those faults form and what are the stresses required for them to form. So a fault is simply a shear failure at a large scale. And something very important is that because it is shear failure, notice that there is a displacement of the rock along the fault plane. So for example, this point is that point over there. So here, for example, there is a mismatch now of this length, and there is a relative displacement with respect to each other. This is different to what is called a rock joint. In a rock joint, sometimes when rocks also get exhumed, that means that some of the overburden, it gets eroded with time, and as rocks cool off, the rock may also break in tensile failure, but this is not a fault. This is a joint in which, if you take a look at those 2 points, they haven't moved relative to each other in direction perpendicular to the failure plane. So that will be a joint. This one will be a fault, and it is just an event of shear failure. Okay, so I have some cool pictures about faults over here, and I should include a few ones that I took recently in a field trip. But let me find the ones I want to show. Okay, that's a much better T-Rex over there. All right. So here you have an example of a fault. This one is pretty good. You see how there is a displacement relative to the fault plane. Like this point over here is displaced about, I don't know what, 10 feet, probably a little bit more, with respect to this point. That's what is called the fault throw. How much it moves with respect to the other side is called the fault throw. And that we're going to see later on that depends on, in the direction in which it moves, it depends on the directions of the stresses. And in this example, it's very obvious to see the fault, right? You go to the outcrop, and you see the fault right away. However, how do you map faults in the subsurface? Seismic, very well. So this is the example that we saw in the previous image. So this is seismic, right? So you recognize the different horizons at which the P waves bounce back, and then these lines are drawn. They weren't there before, but somebody that knows about seismic interpretation drew those lines, recognizing that there was a fault in there. However, with seismic, we can recognize faults, but relatively large faults. What do you do with smaller faults? Let me get out of here and just write that down. Any idea? Subsurface. Okay, so large scale, seismic, and small scale. You can do it with wellbore images. I don't know, you have taken already the class from Professor Torres Verdin, but there you will see that you can take image from wellbores that allow you to see faults around the wellbore. So let me go to an example over here. This is an image similar to this one or to that other one over there, okay? And here you have the image, as we call it, wrapped around the wellbore. That's what you actually measure. But sometimes in order to visualize this in a 2D space, you plot this unwrapped version, which is 360 degrees. If you know this from the top, you will see that here it says north, east, south, west, and north. So this is the unwrapped version of the wellbore image. And if you wrap it, then that will be the wellbore. Well, in wellbores with this formation microimaging, either if you do it with electric resistivity, like those that you see over here, those are electric resistivity, or this one, which is with ultrasonic wave velocity, you can measure either resistivity or travel time, and whenever you have fractures, there's going to be an anomaly in that measurement that's going to signal that fracture very well. And a fracture that appears in the wellbore in these unwrapped plots is going to look like a sinusoid, because let me draw it over here. I basically want to do this drawing of the wellbore. Basically what you do is you get a wellbore, you image a wellbore, and if there is a fracture going through this wellbore, that's going to be a plane that cuts the wellbore. And what you look at is this ellipse. And when you start imaging, let's say that the north is in this direction, the east is in this direction. You start this point in the north, you are in the middle. You go in this direction, you are at the lowest point. You come back, you are at the middle again, and then you go up, and then you're at the top. So when you unwrap this image, then it's going to look like a sinusoid. And the amplitude of the sinusoid is going to tell you how steep the fracture is, or the fault is, and where the peak appears in this sinusoid also is going to tell you in which direction the fault is dipping. All right, so with these two methods, you can get to know pretty well where some of the faults and fractures are. The limitation of the wellbore method is that you cannot map all the faults, right? You just map the ones that are close to the wellbore. All right, let's see why. Before we dive into the faults and all the numbers that we need and all the names that we're going to learn, let's see why we need to map faults. This is what the real reservoir looks like in a sequence of sedimentary layers which are faulted. There are some reservoirs that are more faulted than others. For example, in unconventionals, often you will see some faults, but probably not as many as if you go to offshore conditions. In offshore conditions, you may see a lot more faults than in some more relatively quiet areas without much tectonic displacements or lateral displacements. But we need to take into account these faults, because these faults, as you know, sometimes they can trap hydrocarbons. So if you know where the fault is, you can guess where you could find oil or gas. And also we want to know where those are, because when we lower the pressure of the reservoir or when we inject the fluid, we want to know if we are altering the state of stress of those faults. Are you guys familiar with induced seismicity. I think we talked a little bit about that. But induced seismicity, for example, in Oklahoma, the large ones, were caused by destabilizing some deep faults because of injecting brine at a constant rate and without checking too much about what was increase of pressure. And in some cases, the increase of pressure was so large that it destabilized the fault, and the fault that was originally at equilibrium slides again. And as it slides, it releases energy and creates induced seismicity. And in order to avoid that, we need to know very well what's going on in here. And another application of this, as we said, sometimes these are very good traps for hydrocarbons, and you don't want to mess up with the trap. Imagine that you want to do enhanced oil recovery, and you start pressurizing your reservoir, and all of a sudden you lose your trap, and all of your hydrocarbons, they leak to the surface. That's not an ideal scenario, right? Let me show you an example to show to prove that that can happen sometimes, but we don't want that to happen. And this is an example called the Frayed Oil Field. So this is in offshore Brazil. What do you think that is? That's not a video. And so here we have a crack, right? We have a crack, and we have oil spilling out of that crack and going into the seafloor. And I think the case for this one was a case of fault reactivation, that it went all the way up to the surface. And after some time, they killed it, so now you see that it has closed and there is no leak anymore. Well, in also order to be able to do that, you need to know about fault mechanics. And I think now this back here is leaking again. All right, so where is, I hope that you can see that this is the plane of the fault, right? This is the plane of the fault. And I remember that we said before that failure is very important because it changes your permeability, it changes your transport properties. And in this case, you can see right away how it changed transport properties, and you had oil spilling into the seafloor. All right. Well, then let's try to understand the others. We're going to apply some math to all of these and all of what we have learned. Oh, by the way, today we have seen all the basics that we needed. Today we start with applications till December 12th or 10th, I don't remember. And the first application is about faults. All right. So we're going to start by doing a few definitions, and these definitions are related to the fault geometry. All right, so let's say that, what's that? YouTube? Wait a minute. Helicopter. Did any of you do an internship or something in an offshore platform? Yeah? Does it look like that? All right, okay. Let me come back to this. Okay. Have you heard Professor Van Noort's joke about the guys from Halliburton in the offshore? Okay, I'm not going to say, but you ask him, okay? You ask him. It's a little bit politically incorrect, so You tell Dr. Wanor to tell you that joke. He'll tell you. He's a good joke teller, so he's going to be better than me. Okay. So we have north, east, and down. And let's say that we have a block here. And here we're going to have a plane that cuts this block, which is going to be the fault. All right, so we're going to define a few things here. So this is a cut on the cube. And if I were to drop a drop of water somewhere over here, it will fall in this direction. This is the steepest direction in this plane. All right, the first thing we're going to define is what is called the strike of the fault, or in general of any plane in here. And this is going to be the angle. This is the north. It's going to be the angle between the north and the intersection of this plane with the horizontal plane. So in this particular cube, this is a horizontal plane. And this is our fault, or in general, fracture. Again, this line, which is the line of strike, is going to be the intersection between a horizontal plane and the plane of the fault. And the angle between the north and that line is the angle of strike. All right. In order to define a plane in 3 dimensions, we need 2 angles. So we need one more. And this one is going to be the angle between a horizontal plane and the steepest line in the plane. And this one is going to be the dip angle. So this is a line on the horizontal plane. And how far that goes into the steepest line, that is going to be the dip. And with these 2 angles, I can fully characterize the orientation of any plane in 3 dimensions. There is, however, there are some conventions about strike and dip that we have to mention. For dip, it's relatively easy. The angle of dip is going to go from 0 to 90 degrees. And in addition to that, sometimes you could add to that angle in which direction it is dipping. For example, this dips in direction southeast because it goes down, or it dips in direction southeast. Can you see that? So this is the north, this is the east, and this is the south. This one goes down into the southeast direction. So for example, I could say that this one, just from eyeballing, probably this 40 degrees southeast. That's a dip. For the strike, there is a little bit more of variability in that angle, and we're going to see that. Let me move this up so I can fit everything in here. Okay, this is going to be the strike. There is what is called the Quadrant Converge convention. And in this convention, what you do is you refer to this angle in a particular quadrant. And what I mean is, like, for example, this fault and this strike is between the north and east. And this is a lot easier in the field, because in the field sometimes you go and you're with your compass and you're looking at your compass and you say, okay, well, this fault is at, for example, let's say this one, 30 degrees from the north towards the east. And you just write that. So from the north, 30 degrees towards the east. You could also say this one is from the east 60 degrees to the north. It's the same thing, but usually you will go with a smaller value. But both of them are fine. This one works very well when you're in the field. However, if you want to give this value to a computer, it's not going to like it, because it has letters inside. And if you want to take, let's say, the tangent of this angle, you need to do something else. So that's why there is also what is called the Azimuth Convention. And for this one, you always measure the angle from the north and clockwise. So let me write that here. So for this particular case, we could say that that angle is in the Azimuth convention. You always have to write 3 digits. It's going to be 0, 30 degrees. And you could also take a look, or you could also measure, like, you know, if we continue over here, you could also measure 180 plus 30. We're going to see later on that there is a convention for that too. But for this particular case, that's going to be the angle, 30 degrees. And then this one goes all the way. So usually, again, in this convention, the angle will go from 0 to 90 degrees. In the Azimuth convention, it's going to go from 0 to 360 degrees. And always with 3 digits. And now, with this number and with this convention, you're going to see that this is going to be a lot easier when we have to put this into a computer and we have to compute sines, cosines, and all of that. All right, strike and dip. We need this in order to start applying this to reality, okay? Because we measure these faults in real system, where there is a north, there is an east, and also the stresses, they have a real orientation. Take a look at this. Anyone knows what this map is? North Sea is in the tectonic map of the North Sea, but what are those lines? Those are all faults. So the thicker the line, the bigger the fault throw, and the direction of the lines is telling you in which direction the faults are. So in many of these cases, the direction of the faults is going to tell you probably where also you may have oil accumulation, and also in which direction you have the local stress, the minimum stress. And for example, here in the middle, you see in blue what is called a graben. That's a section which is the lower section between 2 normal faults. But you can see very well over here what is the direction of the faults. So faults, they have an orientation, and we need to know that in order to do any analysis. Okay, there is one more thing about geology that we have to learn before we move on into continue with geomechanics. And this is what is called an stereonet. Are you guys familiar with stereonets? Yes, some of you are. Remember, all of this geology knowledge, likely you're not going to get to apply it later on, but you're going to talk to geologists. They're going to show you maps and are going to, you need to work with them in order to have good solutions for the complex engineering problems that we face in petroleum engineering. So in order to talk to them, you need to know all of this. All right, so in stereonet, it's a 2D representation of a 3-dimensional plane. It's just an easier way to look at faults. And in these stereonets, what you do is, first I'm going to draw the 3D stereonet, although the actual one is 2D, okay? But we'll first go to the 3D to show the concept. But in these stereonets, what you do is you plot in a lower hemisphere projection. So this is like a cup in which here we have the north, the west, the east, and here the south. But now this is a semi-spherical cup where the bottom of this cup is round right here. All right. So can you see this 3D dimension, 3D figure? All right. So now we're going to put the fault in there, the plane that we had before. So the plane that we had before had a 30-degree strike, and it was dipping towards the southeast. So what you have to imagine now is that plane cutting through that lower semi-sphere. And it's going to cut it not here at the bottom because it's at some angle, but it's going to cut it somewhere over there. And I'm going to show you an animation of this later, guys, but first let's try to do it with drawings. This is not what we're interested in, okay? Let me do the 2D version so I can explain myself a little bit better about what you're seeing. So in the 2D version, we do this like this. I think in many of our plots, we're limited by 2D paper. But I think as we move in the future, we need to move more into 3D plots or 3D animations. And probably, within, 20 years, we will not use stereonets anymore. But they're useful to summarize data. But sometimes it's better to see it in 3 dimensions. But it's useful other times to see in 2 dimensions. All right, so the strike, now in a 2D version, looking from the top, is going to be that line. And where it intersects the lower hemisphere projection is going to be that line. All right, so the objective of the stereonet is, instead of looking at the plane or at the line, is just to simplify everything and look at just a point. And in order to do that, any plane or all planes, they have a perpendicular line to them. That's what we define them. You define a plane either with 2 lines or with 1 line perpendicular to it. And this plane is not going to be the exception. And perpendicular to this, there's going to be a line that's going to hit this lower hemisphere projection somewhere over here. And my 3D drawing is not great, but what you will see in this direction is that if it has a dip of 40 degrees, so it's going to be somewhere over here. And this is the point that we want to plot. So the stereonet is going to reduce all planes to just 1 point. And let me show you with this, with my little toy, that you can also use it. You can make one of your own and use it in the exams. This is the plane, okay? So the plane, we said it has strike of 30 degrees. That will be strike of 0 degrees. This is strike of 30 degrees. And now the dip is 90 degrees. If I take it all the way over here, that would be a dip of 0 degrees. And for this one, we said the dip was 40 degrees. So let's say somewhere over here. So what we want to plot is the tip of this line and where it hits the lower hemisphere projection. But you know, just with one point, we can represent any strike, any dip. For vertical fractures, the point is going to be in the outer edge of this circle. For horizontal planes or close to horizontal planes, it's going to be closer to here. All right. So you can use that toy, or also you can use another thing, which I have somewhere over here, which is, let's find it. Okay. It's an animation in which you can add points to this stereonet. So this is stereonet projection. Let me make it bigger. Then we said points closer to the middle. This is no dip. And then we were trying to see this plane of us with strike of 30 degrees. Let me see, was 30? Yes, 30 degrees and dip of 40 degrees. So let me find that. I'm at the strike, and now I need to get the dip. Okay, so the dip is going to be somewhere over here. Okay, so I'm going to make a few just to make it more obvious and to show the power of this stereonet. So these are the planes I just created, and this is the normal line perpendicular to that plane hitting the lower hemisphere projection. And what these are those points, right? Those are the planes. The north is over here, but we want to simplify this. We don't want to look at the planes. We want to look just at the points. And you will see that why that later on. But to these stereonet plots, we're going to add some other things. We're going to add computations of, for example, what is shear stress divided normal effective stress, and make a color plot of that. And all of that together is going to tell us, for example, if those faults are close to shear or not. So I think we're pretty close. I'm going to end here, but just with one example, just to show these guys. I want to show you this example that I just said, and this is right here. Okay. So okay, so here you see we have what we just learned. This is a stereonet projection. All of those dots are faults, and depending where those faults are or how they are oriented, for this particular case in red, it means they are closer to shear failure. In blue, it means they are further away to shear failure. And that's going to depend on how these faults are oriented. In this particular case, these faults oriented in this direction are the ones that are going to reactivate in shear. All right, guys. I'll see you on Wednesday. Don't forget to go to the lab. Again, long pants, closed-toe shoes.